good. Yeah.
Welcome to the seminar of the IAU Commission, the Local Universe. And today we have a very interesting talk by Michael Schulreich from the Technical University in Berlin about connection between supernova and the local bubble and deep sea radioisotopes. So this is new thematics in our seminars. So you are very welcome, Michael, to present your talk.
Thank you very much, and welcome and good morning again, everyone. So first of all, I would like to thank the organizers for giving me the possibility to give a talk in this esteemed seminar. And so, as you know, the sun and its surroundings are embedded in a cavity of low density, high temperature plasma, delimited by a shell of cold neutral gas and dust, the local bubble. Its detection was accomplished in a number of ways, including sodium-1 and calcium-2 absorption lines and dust extinction mapping. The idea here is to check whether the light of nearby stars is reddened and extinguished by the presence of a dense and dusty obstacle, such as the outer shell of the local bubble, or whether it contains the said absorption lines, and if so, with which equivalent width. And if this is done for a large number of stars, for which accurate parallaxes are available, one can create very detailed three-dimensional maps of the local bubble in dust and gas. And it turned out that the local bubble has a rather irregular shape and that it is essentially empty of neutral gas out to between 150 parsecs in the galactic plane. At higher galactic latitudes, where this sampling is sparser, its size is less well constrained, but certainly extends farther out than in the plane to distances well beyond 100 parsecs. Furthermore, it was realized that much of the easily absorbed soft X-rays that reach Earth from all directions, as shown here for the energies of 1/4 keV, must come from the local hot bubble plasma, whereas the rest of the emission, which amounts to about 40%, is produced within the solar system through charge exchange reactions between the heavy ions of the solar wind and neutral hydrogen and helium in interplanetary space. The local bubble also plays an essential role, presumably, for shaping our interstellar neighborhood, as presumably almost all nearby star formation was triggered by its expanding outer shell, as was recently claimed by Zucker and co-workers. Regarding the origin of the local bubble, it is now widely agreed that it was created by stellar winds and supernovae from nearby massive stars. Paradoxically, no cluster of massive stars could be found inside its current boundaries. So there must have been a young star cluster that have passed through today's local bubble region in the past and provided enough supernovae to inflate the local bubble in the process. From previous studies in our working group, the most probable source of most, if not all, of the supernovae has turned out to be the Scorpio-Centaurus complex, which is the closest OB association to the Sun at a distance between 100 and 200 parsecs. However, these earlier studies were still based on data from the Hipparcos satellite and not yet on data from Gaia, which, as you also know, is superior in terms of sensitivity, sky coverage, and astrometric precision. And to remedy this, the calculations I'm going to present you today in this talk are all based on a field star contamination clean sample of candidate members of the SCOSEN complex selected by Kevin Luhman in 2022 using the early installment of the third data release of Gaia. And to assign the SCOSEN stars to the individual populations of Ophiuchus, Upper Scorpius, V1062 SCO, Lupus, and Upper Centaurus Lupus and Lower Centaurus Crux, Luhman looked for clustering in proper motion offsets, parallactic distance, as well as celestial coordinates, and at the star's positions in color magnitude diagrams. And these are the members he was able to find and for which Gaia measurements for the radial velocities exist. The stars here are color-coded according to the population they belong to. And for a better orientation, I have projected the heliocentric galactic Cartesian coordinates of these stars onto slices through the 3D dust density distribution of the local interstellar medium, as derived by Rosine Lallement and co-workers from measurements of the starlight absorption by interstellar dust. The color coding here is black for high dust densities and light yellow for low ones, and you will immediately recognize the outer shell of the local bubble from these maps. And what I also want to mention is here that these slices are along the plane through the sun, here parallel to the galactic midplane, parallel to the rotation plane, and parallel to the meridian plane. So now that we had a suitable, up-to-date stellar sample, we could try to uncover those core collapse supernovae that created the local bubble, which essentially means answering these three questions. And for the first, for calculating the number of missing stars, that is of stars that have already exploded, we fitted the initial mass function of Krupa, this time also taking into account the studies which indicate that 95% of all type 2 supernovae have initial masses between 9 and 22 solar masses, and that the last supernova explosion in the local bubble volume should not have occurred less than 0.5 million years ago. This constraint can be made on the basis of the observed absorption features of the lithium-like ions carbon-4, nitrogen-5, and oxygen-6. We ended up with 14 supernova explosions in total, of which 13 occurred in UCLLCC and 1 in V1062 SCO. And when these explosions occurred is also related to the initial masses of these stars, since these dictate their lifetimes. And for estimating their lifetimes, we linearly interpolated between the rotating stellar evolution models of Ekström and co-workers. And if one then assumes that all the stars in the population are born at the same time, then the explosion times are simply the differences between the lifetimes of the stars and the population ages, which were also provided by Lumen. And for estimating or for setting the initial masses of the stars, we took those values for which the IMF reaches its mean value. For the intervals, we have derived such that they contain exactly one star each, which always gives the distribution with the highest probability. So the only thing missing now are the supernova explosion sites, or in other words, the trajectories of the supernova progenitor stars. And to obtain these, we perform test particle simulations in a realistic Milky Way-like potential using the Galactic Dynamics Python package GalPy. But we did not perform one back calculation per population, but 10,000, each one considering a realization of the population based on the observational errors in positions and velocities of each member star. So in these maps here, you just see the mean positions of the stars without the uncertainties. But these we have now taken into account for our back calculations, as I just said. So this is more a Monte Carlo-like approach. And at the explosion time of each supernova, we now paused all our back calculations of the corresponding population and computed the six-dimensional phase-space probability density function for the population's combined realization. So for all of its realizations at once. And since 60 plots are notoriously difficult to look at, what I show you here are just projections onto all sorts of two-dimensional planes, for, in this case, for UCLLCC, at t minus 10.16 million years, which is the explosion time of the very first supernova in our model. The red crosses here in this map show the projection of the bin in which the full six-dimensional PDF reaches its maximum value. So from a purely stellar statistical point of view, a supernova at this particular time should have originated from a massive star at approximately this location with approximately this peculiar velocity. And using this data, we can now compute again with GalPy hypothetical, or so to say, pseudo trajectories along which the missing stars have migrated along with the other members of the population still present today. And so that you can see how such a test particle simulation looks like, I show you here a movie of an exemplary one, and not just for a single population, but already for the entire SCO-SEN complex. This movie here starts at t minus 20 million years, which is the birth time of the two oldest populations, UCL-LCC and V1062 SCO. And the other populations are born at different times later. And when this happens, I simply let them appear here in this movie at their time of birth. The colors correspond to the peculiar speeds of the stars. And I also show the trajectory of the sun, which is here this empty circle, and also the pseudo trajectories of the local power progenitor stars, which break up at their explosion sites. And when this happens, I also included a simple analytical reproduction of the resulting local bubble using the Weaver et al. Adiabatic wind solution. So this gray sphere here represents the expanding outer shell of the local bubble. Of course, this approximation completely ignores the wind-driven phase of the local bubble. Likewise, a homogeneous background medium is assumed, hence this perfect spherical shape. And one replaces discrete supernova events with a continuous high-energy wind by defining this mechanical luminosity equivalent as the ratio between the explosion energy of a single supernova and the average time delay between successive supernovae. Yeah, and this is the final radius of the local bubble that is obtained from these parameters. Completely independent of other observational channels, it is also possible to draw conclusions about near-Earth supernova and therefore about the origin of the local bubble from measuring long-lived radioisotopes, which, however, have lifetimes short enough to be excluded as leftovers from the solar system formation period. And one of the most promising in this context is RN60, because it is predicted to be produced in copious amounts by supernovae, and because the natural abundance on Earth is far below any supernova-induced signal. Furthermore, RN60 has a half-life of 2.6 million years, which is long enough to survive significant traveling through the local interstellar medium. And RN60, as well as other radioisotopes, are believed to be delivered to Earth while being condensed onto dust grains. And as already teased here by this animation, to date, RN60 has been found in deep sea ferromanganese crusts, nodules, and sediments, including fossilized bacteria from all around the world, as well as in Antarctic surface snow. And the most recent and sensitive of these measurements, all using accelerator mass spectrometry, showed not only a peak of RN60 at a depth corresponding to about 3 million years, which has now been known for over 2 decades, but also a second separate peak about 7 million years ago. And in addition, low but significant RN60 influx over the last few 10,000 years. Furthermore, RN60 has been found in lunar rocks recovered in the course of the Apollo missions, as well as in observations of the diffuse galactic gamma ray emission associated with its decay, and in galactic cosmic rays. 2 other radioisotopes that are also released in large amounts by supernovae are aluminum-26 and manganese-53. Aluminum-26 even by the preceding stellar winds. And unlike RN60, both isotopes have a continuous influx onto Earth, originating from cosmic ray spallation reactions, in the case of aluminum-26 with the argon in Earth's atmosphere, and for manganese-53 with the iron in interplanetary dust particles. And it is these high cosmogenic backgrounds that makes it extremely difficult to isolate or even to detect contributions from stellar nucleosynthesis sources. In the case of manganese-53, however, this seems to have been accomplished, again in deep sea ferromanganese crusts, showing elevated levels of manganese-53 for the same time range as the younger RN60 signal. And also undecayed interstellar plutonium-244 has been recently detected in deep sea ferromanganese crusts, although the low time resolution of this measurement does not allow to see matches with these 2 clearly defined RN60 peaks. The sources in which this very long-lived radioisotope is produced under explosive conditions are still under debate. In the closest selection are currently neutron star mergers, sometimes also called kilonovae, and very rare types of supernovae, such as magnetorotational supernovae. And also note that these measurements here in the uppermost crust layer suffer from anthropogenic, that is man-made background originating from the atmospheric atomic bomb tests in the 1950s and 60s, which is here already subtracted. And all these measurements now pose additional constraint for our local power formation scenario, which we further investigated by means of 3D hydrodynamic simulations. And for these simulations, we used the publicly available adaptive mesh refinement code RAMSES. The computational box is a cubic cutout of the galactic disk in the solar neighborhood with a side length of 800 parsecs that co-rotates with the local standard of rest. And on this domain, we achieve sub-parsec resolutions. The inhomogeneous background medium has been tailored by us to be in both in hydrostatic and in thermal equilibrium on the basis of the same gravitational potential we already used for the stellar trace specs. The free parameter in this context is the density in the galactic midplane. So we conducted a series of simulations in which we varied this density between 0.1 and 1 hydrogen atom per cubic centimeters in steps of 0.1 and found that for 0.7, the calculations best reproduce both the observable properties of the local bubble and the radioisotopic measurements available. Therefore, I will focus on this best fitting round for the rest of this talk. We account for collisional ionization equilibrium cooling of the gas, which we assume to have solar abundances everywhere. And both the local power progenitors as well as the sun are treated in these simulations as collisionless particles, which move along the trajectories already calculated with GalPy. The massive stars blow stellar winds, which depend not only on the initial masses of the stars, but also on their instantaneous ages. And as such, all the stars go through a main sequence and the red supergiant phase, and only the two most massive ones through an additional Wolf-Rayet phase. And when their lifetimes have run out, they explode as supernovae. The sun or Earth, between which we cannot distinguish due to the limited spatial resolution, assumes the role of a moving detector in these simulations for the radioisotopic fluxes that stem from the stellar feedback. And talking about these radioisotopes, these are the four already mentioned ones we included in our simulations and treated them as passive scalars, decaying passive scalars, which are quantities that behave like ink drops that are dispersed in a liquid. Only aluminum-26 is released via stellar winds, for which we use the yields of Ekström and co-workers, and the supernova yields for aluminum-26, manganese-53, and iron-60 were taken from the rotating recommended model of Limongi and Jeffy. In order to consider only the amounts released in the course of the formation of the local bubble, we set their initial concentrations equal to 0. So our model always gives the lower limits. For plutonium-244, on the other hand, which was presumably released by a kilonova prior to the formation of the local bubble, and thus was already present in its region of influence in an unknown amount, we first assumed an initial concentration of 100%. And after running the simulation, we then scaled the concentration so that the measured influx of plutonium-244 integrated over the last few million years is matched perfectly. And with this approach, this allows us not only to track the turbulent mixing of plutonium-244 in absolute numbers, but also to draw conclusions about its initial concentration. And what I want to show you now is a movie of our fiducial simulation, or more precisely an animated volume rendering of the hydrogen number density associated with the local bubble. So the inhomogeneous background medium has been already masked out here. The 14 dots you see here are the 14 local power progenitor stars at the start of the simulation T minus 20 million years. And you will see the sun coming in from the left as soon as I start the movie and the box begins to rotate. Please also note that these dots do not disappear, even not when the stars explode as supernova. So they just keep going on the trajectory the star would have taken if it had lived until today. So don't be surprised about that. Of course, as soon as the star explodes, its feedback in the simulation stops. So rather see these points as a rough indication where the rest of the population is located at each instant of time, as these few stars trace the parent populations quite nicely. So now enjoy the show. So here this is the sun coming in. At the moment we are in the wind-driven phase of the local bubble. The massive stars blow energetic winds, most of the individual wind-blown bubbles quickly merge and assume a rather cometary bow-shock-like shape since they move at supersonic speed with respect to the background medium. Now the supernovae go off sequentially, they inflate the local bubble, the sun crosses its outer shell about 4.6 million years ago, and finally takes its position rather close to the center of the local bubble. Now, at the present time, we make a camera trip into the interior of the local bubble and stop very close in front of the sun. And now, finally, we make another 360-degree turnaround to see how it looks like in this local hot bubble medium. You see quite much structure here, which is not surprising, since as the supernova blast waves reach the surrounding supershell, they get asymmetrically reflected from it, interact with each other, and this acts like a spoon that steers up this medium and keeps it in a highly turbulent state. What we can now also extract from these kinds of simulations are the local interstellar fluxes of the radioisotopes, that is, the fluxes at the heliosphere boundary as a function of time. So blue is aluminum-26, purple is manganese-53, red is iron-60, and green is plutonium-244. And these vertical dashed lines indicate the supernova explosion times. And these profiles can now be converted and rebinned into density ratios that can be directly compared with the available measurements in the terrestrial archives. So the measurements are the dots with the error bars, and the histograms are the simulation results. In general, we achieve a very good agreement considering how many hard-to-constrain parameters this local bubble model is based on. According to our simulation, the younger peak is generated by the supernova blast waves together with their reflected shocks. And we are also able to reproduce quite precisely these recent influxes, which in our model are generated by the yet undecayed turbulence in the local bubble cavity. Even though the last supernova explosion has already occurred more than 500,000 years ago. For aluminum-26, the contributions coming from the stellar feedback processes, so these dark blue histograms, are hidden in the high cosmogenic background, the gray-blue histograms. This was already predicted by Feige and co-workers. And the only major discrepancy we actually get is a quite huge one of 10 orders of magnitudes, by which our simulations overestimate the measured plutonium-244 over iron-60 ratio for the time range 4.6 to 9 million years. But we see this bad match actually as a strong indication that the solar system, before entering the local bubble about 4.6 million years ago, must have passed through a medium that, similar to the volume of the local bubble, must have been almost empty of plutonium-244 atoms, and thus presumably of gas per se. And a very probable environment to encounter such conditions would be another superbubble, a neighboring superbubble, which has not yet been included in these simulations. And a very promising candidate in this context is the Orion-Eridanus superbubble, which is also the closest superbubble to the Sun. There's still no agreement in the literature about its exact geometry, but many observations suggest that its long axis is nearly parallel to the galactic plane, with its near end about 200 parsecs away from the Sun, and its far end somewhere around Orion. Where exactly is quite uncertain though. And one formation scenario discussed is sequential supernova activity along the so-called blue stream of massive stars, which is also roughly parallel to the galactic plane. And particularly interesting here is this so-called Orion Big Blast, which was a major supernova event in that superbubble 6 to 7 million years ago. And why this is interesting, well, there's this remarkable temporal coincidence with the older iron-60 peak, the same time range actually. So there's a good chance that when our solar system crossed that superbubble, that it was exposed to this and probably also to other supernova events during that time. This is something we will certainly test, a hypothesis we will test in future simulations. And on this last slide, not counting my summary, I show you the presumed birthplaces of Scosen subgroups with respect to the evolving local bubble. So in particular, you see here in purple in each panel the enveloping surface of the local bubble, together with the 3 sigma error ellipsoids of the centroids computed for the 10,000 realizations of all the populations that are not the progenitor populations. So here for Aposcorpius, for Lupus, and for Ophiuchus at their respective birth times. And the fact that in all cases, the outer boundary of the local bubble and therefore strong shock fronts are never far from the population birthplaces. In fact, they have very recently passed over them, suggests that the local bubble was indeed involved in the formation of these populations. Of course, this is just a rough first look, and if one wanted to do this properly, one would have to include star formation or first interstellar clouds in the simulations you have just seen, and then follow the star formation self-consistently in these clouds. But this is something we will certainly do in the future. And with this outlook, I would like to come to an end, but not before advertising the companion paper to this talk, which will come out very soon in Astronomy and Astrophysics. The preprint is already available on the archive at this link. Thank you very much for your attention.
Thank you very much. Indeed, very impressive study, and the simulations. Who have questions? I see experts of supernova investigations are here, so you are welcome to ask.
Can I confirm the time scale of the sun's motion to pass through the local bubble?
Yeah. You mean so the simulation? So the whole simulation lasts for 20 million years, and that's also the birth time of the two oldest populations. So during that time, so before 10 million years or so, there was this purely wind-driven phase of the local bubble. I mean, you could still already call it the local bubble, since you have already several merged wind bubbles, which is actually already a super bubble. But after that time, so about 10.16 million years ago, the first supernova in this model occurred. And the solar system actually crossed the local bubble 4.6 million years ago. And then, of course, then it was possible that these individual supernova blast waves were able to reach the solar system and therefore implement these radioisotopes in the deep sea.
So it means that another 4 million years or so will be required to pass through the local bubble.
Yeah, exactly. So therefore, the younger signal cannot have something to do with the local bubble, but must have something to do with our surrounding medium, so to say. And we think that the second signal was produced again by the contact with of the solar system with another superbubble, so to say, or at least with some interstellar cavity in which, again, supernova blast waves could propagate and reach the solar system directly.
Okay, thank you.
So, Yusuke?
Yes. Can you hear me?
Yes.
Hi, Michael. So I'm Yusuke Fujimoto. Very nice talk. Thank you very much. Actually, I have worked on the same topic, but with a galactic scale. I have performed a galactic simulation with Army 26 and IM 60. So
I know them. Yeah.
So,
yeah.
Oh yeah, thank you very much. Yeah, I know. Yes, actually, I know your recent paper posted on archive, and you cited my paper. Thank you very much. So yeah, actually, I have questions about the simulation setup. So what kind of initial mass function do you use? So you say that's a Kruger initial mass function because
Yeah.
I think at this scale, I think the choice for the initial mass function very so that the initial mass function may changes the result. Have you ever checked? So have you performed with different initial mass functions?
No, actually, we already did earlier studies in which we used different mass function, the messy IMF. Actually, this is not so not such a well-known IMF, but as far as I know, the Krupa IMF has not a is more or less a broken power law. So you have depending on the initial masses, several sections of the IMF in which the scaling exponent changes. So of course, since we already considered stars in a rather narrow mass range. I mean, we only considered the stars between 9 and 22 solar masses, since in this mass range, 95% of all type 2 supernova progenitor stars lie, in contrast to your study where you have a much broader, I mean, you considered a really broad mass range. But in our case, I mean, the only stars we actually implemented in these simulations are these 14 local power progenitor stars and the sun. And therefore, we consider this IMF to be sufficient, at least for these few progenitors.
I see. Thank you very much. And also, I have another question about the estimations of iron 60 flux onto the Earth. So,
yeah,
could you
yeah.
show me the?
So I have some actually here. If you have seen the publication, you already know that. So these are now the, so to say, the initial parameters for the simulation for the stars, at least for this. These are the parameters for the 14 local power progenitor stars. So here are their explosion times. These are the positions at which they explode, their explosion sites. This is the distance to the sun when they explode, and these are the final peculiar velocities of the stars, their initial masses, and this. Now I come to your question. These are the yields, the supernova yields, the ejected masses. And we didn't, of course, use, I think, I don't know if I remember correctly, you used for each star the same supernova yield, right? Or did you also scale them? So we scaled our yields according to the stellar evolution model. So we used this, the Limongi and Jeffy supernova models. And so these are the ejected masses for aluminum 26, manganese 53, and iron 60 of each of these local power progenitor stars. And you see this can quite vary, and therefore these fluxes I have shown before, these flux profiles, where do I have it? The variation of this flux profile, so that you here, for example, have this slight bump here. This comes from the variation of the supernova yield, so to say. So of course the spikes are always produced when a supernova blast happens. The spikes are very shortly after the supernova explodes. So these vertical dashed lines are the supernova explosion times, and very slightly afterwards you get, of course, this spike because the local power volume is highly diluted, and therefore the supernova blast waves can propagate very quickly within this volume and therefore reach the solar system almost instantly, so to say. And so this has been actually fine-tuned, so to say. We included the yields from stellar evolution models and didn't use constant ones for every supernova.
Okay, thank you. So last questions about magnetic field. So I know you're using the Ramsey code, and I know the Ramsey code has a functionality of magnetohydrodynamics. So do you expect
at the moment we haven't included
change?
Yeah. At the moment, we haven't included them, but so for this study, we haven't included it. But at the moment, we are running simulations with the magnetic field. I mean, what I can already say now, or what we expect is, of course, the magnetic field would add to the external pressure and tension, and would therefore favor expansion along the mean field direction. And so the magnetic field would certainly be strongest in the outer shell, in the supershell of the local bubble. This would mitigate shell instabilities and of course, would also impede turbulent mixing. So we would also expect lower amounts of plutonium-244 that find their way into the local bubble, because I mean, the plutonium-244 is not released, at least not in this model, not released by the co-collapse supernova, but we assume that it was already present in the local bubble volume before the local bubble has formed. So all the iron-60 that is within the local bubble has been mixed over the contact discontinuity in the supershell from the surrounding medium. So this would probably change a bit. However, the local external B field is about 1.6 microgauss and is therefore probably too small to have a big dynamical impact on the evolution of the local bubble. And in particular, the field in the interior of the local bubble will certainly be very low. We see this already in these preliminary simulations. So since the field is very low in the local bubble interior, we do not expect any great changes to these radioisotopic studies, because the blast waves don't really feel the magnetic field. It's almost hydrodynamical and not MHD. So therefore, at least in that regard, we don't expect big changes.
Okay. Thank you very much.
You're welcome.
Do we have more questions? So thank you, Michael, for your interesting presentations. Thanks to your efforts, we know more and more about our local universe. So all the best in your future investigations. So thank you very much.
Thank you very much again for the invitation. Bye-bye. Have a nice day.